We are channeling the company's artificial intelligence efforts into one recognizable organization, Qualcomm AI Research. Qualcomm invents breakthrough technology that transforms the way the world connects and communicates. Going beyond mobile chipsets, we're inventing AI technology that can be used across a wide range of products and industries, from mobile and automotive to smart homes and cities, ultimately changing the way people live for the better.
Machine learning has already entered every corner of the Qualcomm enterprise. I personally believe that Qualcomm is uniquely positioned to become a key player in on-device AI, which brings with it tremendous opportunities, such as increased data privacy for users, reliability of service, high speed and efficient use of bandwidth.
Today, machine learning algorithms, such as deep learning, use huge amounts of energy to power them. And as AI increasingly moves to low-power edge devices, energy efficiency becomes all the more important.
The challenge we face in the future is about squeezing as much as computation
Udah. Ya. Oh.
Can you guys hear me? Okay, so I'll wait for Risnander to tell me when to start.
Let's start. Hello. Hello, can you hear my sound?
Yes.
Okay, thank you. Good morning, everyone. Today is the 5th August, and the first for the talk is Jan Fischer from Google AI. And before we start, I would like to remind you that the time is around 1 hour and 13 minutes for you, Fischer. And now is your time to introduce of yourself and continue to your talk. Your time today is your time, please.
Great. So, excuse me. Good morning for those of us in Asia, anyway.
Morning.
Excuse me. Sorry, suddenly my throat needs clearing. So my name's Ian Fischer. I am a researcher at Google Research. Normally I'm located in California, but I've been actually in Singapore for the past few months. So it's also morning for me, which is nice. And today I'm going to give this talk. The talks today and tomorrow that I'm giving are primarily, I would say that these are kind of tutorial-oriented talks. My hope is that I'll give you a pretty good flavor of how information theory is being used in machine learning these days. The latter part of the talk today and tomorrow in particular will cover a fair amount of the research that I've been doing and with some collaborators at Google. But fair warning, as a tutorial, this is going to be a bit math heavy. I'm hoping that for many of you this will be reasonably familiar, but I want to make certain that some of the core techniques that we use to do information use information theory and machine learning are accessible, with like detailed explanations, or at least detailed derivations. With that caveat out of the way, so the title of the talks today are Information Theoretic Objectives and Robust Generalization. And I'll just get started here. So today and tomorrow, we'll be covering this set of things, and it's going to start with this introduction to information theory. And then I'll give you kind of a fairly detailed look at interpreting maximum likelihood, kind of the workhorse of machine learning, as information maximization. Then we'll consider some other info-max approaches that are quite popular these days, before beginning to consider this idea of the information bottleneck and some variations on that. And by the end of the day tomorrow, we should get a chance to get to some very recent work. Okay, so the core of information theory is this idea of an information measure which is called entropy, which we generally write h of x. And so Kl Shannon in the seminal paper, The Mathematical Theory of Communication in 1948, outlined three desiderata of an information measure. First, this measure should be continuous in all of the p of xi, where this is the probability mass function for some discrete random variable x. So if we change the probability of a particular xi, then by some small amount, then the entropy should also change by some small amount. Secondly, if all of the p of xi are equal to each other, so equal 1 over n, where n is the number of different possible settings for the variable x, then h of x should be a monotonically increasing function of n. So as there are more different choices that we can make, this entropy measure should get larger. And then finally, the most complicated criteria here, this is my formulation, slightly different from what Shannon said, but should be equivalent. If x is decomposable into a sequence that we can call like x1 and then x2 given x1 through xk given x1 through xk minus 1, then the entropy of x, h of x, should equal the sum of the conditional entropies, h of x1 plus h of x2 given x1, etc. That's a kind of a bit to take in, so I'll use the diagram that Shannon gave in his paper. If we have this probability distribution where there's three different possibilities for the variable x, one of which happens half of the time, one of which happens a third of the time, and one of which happens 1/6 of the time. But then we can write that as h of 1/2, 1/3, 1/6. So then suppose that if we could actually break that down differently and say that there's actually two different choices that we could make. The first is with 50% probability we choose the first option, and then with 50% probability we have to choose between the second two options. So we get, if we are on the second path, then we end up at this point here, and now we have to choose between 2/3 and 1/3 probability, the second option or the third option. So as you can see, the end result is that there's still the same three options, and they have the same probabilities in both of these. But if we considered those two choices in sequence, we'd have this entropy of the first choice plus the entropy of the second choice, weighted by 1/2 because it only happens half the time. And so these two things need to equal each other. So given those three desiderata, Shannon's entropy theorem says that the only function satisfying these three desiderata is this function, the negative expectation of the log probability of the random variable. So I imagine you guys have all seen this entropy functional before. It's probably fairly familiar. The entropy has units, and the units depend on the choice of some constant scaling factor that we can just incorporate into the choice of the base of the logarithm. So if we use log base 2, this gives us units of bits that in computer science we're very familiar with, and slightly less commonly, but quite common in machine learning, is if you use the natural logarithm, we get nats, which is short for natural units. I'll probably end up saying nats a lot in this talk. So this is the core information measure that Shannon defined. This is the Shannon entropy. It is it's a discrete entropy, so it requires the random variable to be discrete. But when it is discrete, we get a non-negative value out of this, so it's lower bounded by 0. And it's upper bounded by the log of the number of possible different values of the random variable. And that's when there's a uniform distribution over the random variable. Okay, so what is entropy? It's actually a measure of uncertainty. So the higher the entropy, the more uncertain we are about the value of the random variable. So to illustrate this, let's imagine that we have a 29 by 29 pixel black and white image, maybe something that looks like this. And let me actually, is it better for me to be in presentation mode? I should probably switch to present mode, yeah. Okay, can you still see this correctly? Yes, okay, great. Okay, thanks. Okay, so yeah, we have some 29 by 29 black and white image. Here's an example of such an image. And so if we assume that each pixel has a uniform probability of being black or white, then there's 29 squared equals 841 bits of entropy. So that's because one bit measures two choices, and we have 841 different possible choices that we can make. Sorry, it's actually 2 to the 841 different possible images that we can make. Each of those 841 possible choices are independent. And all of these are equally likely, so we have that much uncertainty about what image we'll see next. If we were to just choose one of these random images, we'd be equally surprised by any of them. But what if instead we knew that it was a valid QR code? So here's an example of a valid QR code. This is not a Rickroll. This will take you to Wikipedia. So if it's a valid QR code, we know that, if we know a little bit about QR codes, we know that these highlighted regions are actually going to be the same for every single one of these, the possible images. And so this reduces our uncertainty about the distribution of images to 598 bits of entropy. Similarly, and furthermore, if we actually know the value of another 31 format bits, then the final entropy corresponds exactly just to the data region, of which there's only 4 different choices that depend on the level of error correction. And so in the most, in the version that has the most error correction of the QR code, there's only 208 bits of entropy, even though in the limit where we didn't know anything, there was 841 bits of entropy. So we've actually reduced our uncertainty about what the images are that we might see by 633 bits, which is an enormous amount of information. Okay, so I just said information. So let's talk about the next critical measure of information, which is the mutual information. So the mutual information in full generality looks like this. It's I of xy is this double integral of this expectation over 2 variables of the log probability of the joint distribution over the independent distributions, the marginal distributions. Excuse me. So the mutual information is symmetric. We can see that immediately. If we reversed the x and y, it doesn't change anything here because the joint distribution is symmetric and the marginal distributions are symmetric. It's non-negative. We'll see a little bit more about that later, but you can take my word for it right now. And it's reparameterization invariant, which is a technical term that might be a little bit unfamiliar, so I'll explain what that is a little bit. Reparameterization invariance means that if we were to, for example, multiply the parameters of the underlying distributions, all of them by some scaling constant. Let's say we multiplied like the means and the variances of, let's say, if these were all Gaussian distributions, we could multiply the means and variances by 100 for all 3 distributions, and it wouldn't change the mutual information at all. This is in contrast to the entropy, which if you were to change the parameterization by scaling the distribution parameters by 100 as well, you would get a very large change to the entropy for any reasonable distribution. So entropy is very sensitive to the parameterization, but the mutual information is not. Which ends up being a very nice property for optimization. And so so this is a reparameterization invariant measure of dependency between 2 variables. So these are very nice properties, but it's generally, many people look at mutual information and say mutual information is hard. This is a painful double integral that's completely intractable to compute for any non-trivial x and y that you might be interested in. And so even bounding if we want to lower bound the mutual information, it's known relatively recently that doing so requires exponential samples in the quantity of information being bounded. So that means that if we if we want to get estimate a lower bound on IXY where the true value is 2 bits, well, we only need 4 samples we should only need something like 4 samples. But if we need actually, I'm going to say the wrong thing here, but yeah, if we needed 10 bits, then we'll need 1,000 samples to estimate this. Actually, yeah, so I did say the right thing. So if we have some quantity of information, like I was just referring to in the for the QR codes, where it's hundreds of bits, we'll need 2 to the many hundreds, which is obviously going to not be possible to get that many examples for a particular estimation. But in actuality, these seem like big problems. In actuality, mutual information is really quite easy to work with. This double integral is really easy to estimate using Monte Carlo estimation techniques, and we can get lower bounds on it easily and upper bounds on it easily. And in many settings where that we'd actually care about, these estimates can be very tight. I'm making this as a claim at this point that the mutual information is going to be something that we can work with easily, and we'll see that throughout the talk here. Okay, so what's the relationship between the entropy and the mutual information? So Ixy equals h of x minus h of x given y, which is just a conditional version of the entropy. And it equals h of y minus h of y given x. As I said before, the mutual information is symmetric, and so we see that symmetry in its relationship with the entropy and conditional entropies. And we can visualize these relationships using Venn diagrams. There's important work from the early 90s that showed that it's valid to use these set relationships, because any theory of information theory is in fact a theorem. Any theorem of information theory is in fact a theorem of set theory. So that means we can do this kind of pictorial proving of things where we'll just draw a circle representing the entropy of x and some other circle representing the entropy of y. And now where x, the part of the circle that's outside, the part of the x circle that's outside of the y circle corresponds to the entropy of x given y. Equivalently, we have the entropy of y given x, and then the intersection of the two is the mutual information between x and y. So that says, what this says here is this region here in the center, Ixy, equals h of x minus h of x given y. And actually, let me just double check. You can see my cursor. Can people see my cursor when I move my cursor around the screen? Yes. Okay. Thank you. Great. And symmetrically, Ixy is equal to h of y, the green circle, minus this region, this moon-shaped region, h of y given x. So this is actually a really powerful tool for reasoning about information theoretic quantities. Great. So from this, from both the math and the set diagrams, we can see that the mutual information is the reduction in uncertainty about one variable when you know the value of another random variable. So as I said before, entropy is actually measuring uncertainty, and mutual information is the reduction in uncertainty that we get when we know another random variable. So that means that the mutual information, we should expect that the mutual information will be 0 when the two variables are independent of each other. And that is kind of immediately apparent if you understand the entropy relations here, where we have h of x minus h of x given y. If x and y are independent of each other, then h of x given y equals h of x, and so we get h of x minus h of x, which is 0. Similarly, we can note that there are clear bounds on how large the mutual information can be. The largest that the mutual information can ever be is the minimum of h of x and h of y. That's because the largest it could be for in this equation is its maximum occurs when h of x given y is 0. So the entropy of x is there's no entropy of x when you know what the value of y is, and so at that point we have whatever the entropy of x is minus 0, which is the entropy of x. But since it's symmetric, if h of y happened to be for the value of ixy to equal h of x, then h of y would have to be at least as large as h of x, because otherwise h of y, the largest h of this version of it would be whatever h of y is, where with h of y given x being 0. And so if that was smaller than this, then we'd have a contradiction. So the mutual information is lower bounded by 0, but it's upper bounded by the minimum of the two entropies. Okay, so changing representations here. There's this idea of a Markov chain, which many of you have probably encountered before, which is representing relationships between random variables. And critically, what it's representing is actually lack of relationships, lack of direct relationships between random variables. So a Markov chain, this Markov chain from x to y to z, is saying that the only influence x has on z is completely mediated by y. Kind of using causality terminology there, but so what this is actually telling us is which variables are conditionally independent of each other. So this Markov chain says that x and z are conditionally independent given that you know y. So x perp z given y. And equivalently, this tells us how the minimal factorization of the joint distribution, where so the joint distribution over x, y, and z, we can write. We know that it's valid to write given this Markov chain. We know it's valid to write it as p of x, p of y given x, and p of z given y. And so we're missing in full generality, we would have to write p of z given x, y. But because of this Markov chain, we know that p of z given x, y equals p of z given y. So we can write it this way. So if we know that there's this underlying Markov chain, x to y to z, then probably the most important theorem of information theory is the data processing inequality, which tells us that in this Markov chain, the mutual information between x and z is less than or equal to the mutual information between x and y. And the mutual information between x and z is also less than or equal to the mutual information between y and z. So that's in symbols that might be a little bit hard to just immediately interpret, but if we go back to our set diagrams here, so we have h of x and h of y just like before, and so now we're going to add another variable h of z, and we need to position this correctly, where what the Markov chain is telling us is that z may have some overlap with x, but it can only have that overlap with x where x and y also overlap. So the z circle here does overlap with x, but it overlaps it in the region where y is overlapping with x. And so that means that IXZ is this central region here, this smallest region. And IXY is the same region as before, which includes the IXZ region. And IYZ is this other large region here. And because of the set theory things I said before, this is a correct visual depiction of the data processing inequality. The area of the IXC region is clearly smaller than the area of the IXY region and clearly smaller than the region of the IYZ region. And you can see that that must always be the case. The largest this IXC region could ever be is if it managed to completely fill the IXY region, and right. And the largest is the large if it managed to completely fill the IXY region. Yeah, that's what I wanted to say. Okay, so in this kind of rapid tour of information theory, the Tail Divergence is probably very familiar to you at this point. It says that it's the Tail Divergence between two distributions. We'll call them P and Q, and it's just this expected log ratio between P and Q, where the expectation is over P. And it has this critical property that it's non-negative, it's greater than or equal to 0. And so we can write that as like information terms. This will be a kind of a notation for the cross entropy. So H sub P means that we're talking about an entropy measured with respect to where the expectation is with respect to this distribution P of some other distribution or some random variable. So H sub P of Q of X minus H sub P of P of X. So the cross entropy of P and Q minus the entropy of P. And so this, because the KL is non-negative, this means that the cross entropy is always greater than the entropy. So H sub P of Q of X is always greater than or equal to H sub P of P of X. And this is called Gibbs Inequality. And actually, most bounds on mutual information will rely on this fact. So I'll show you how that's used to derive bounds on mutual information at least a couple of times in these talks. Okay, so we can relate the mutual information then to the Tail Divergence. It's the mutual information is just an expected Tail Divergence. So we have we can write down this Tail Divergence between it's not any Tail Divergence, of course. It's particular forms of Tail Divergences that capture the ratio between the joint distribution and the marginal distributions. So if we have these variables x and y again, then we can have the Tail Divergence of between P of y given x and P of y. And then if we take the expectation over P of x of that Tail Divergence, that is the mutual information. And I'll leave that as an exercise for the viewer to write all that out and see that that's true if that's unclear. And symmetrically, P of x given the Tail Divergence between P of x given y and P of x with the expectation over P of y is also equal to IXY. So these are Tail Divergences, and expectations are just weighted averages where the weights are between 0 and 1, so they're non-negative. So this proves the non-negativity of the mutual information. And a nice thing about information theory is that actually a lot of proofs in information theory are about this easy. Once you know which property of information to apply, it's pretty easy to prove things. Okay, so that's the end of the overview of information theory. I think I should actually stop and just see if I can see if there are any questions that I should be trying to answer here, since that was a very rapid fire overview of the basics of information theory.
Yes, I remind to the audience, if you have any question, maybe please to access the Rocket chat. But if no question, please be sure to continue your slides. Okay.
Okay, so it sounds like there's no immediate questions. Great. So so for the rest of the talk, I'll kind of set up a few notational conventions that hopefully will make it easier to understand what I'm referring to. So random variables, I'll notate with these capital italic letters, X, Y, Z. And as a notational convention, X will refer to the observations. So if we're, as a running example, let's consider a classification problem like ImageNet, an image classification problem. So in this case, X would be the image, the set of images. Then Y will be our targets. So in the classification setting, that'll be our labels. And then Z will refer to some learned representation. And so this is a random variable that is going to represent the capture the information in X and or Y through some learning procedure. So distributions given to us by the universe. I'll notate with a P generally. So P of XY is going to be, for example, the distribution over our observations, X and Y. That's our joint observation distribution. So distributions given to us by the universe will either be something that we can sample from, such as for the observations, or they will be, some true distribution that we'll never be able to get our hands on, that we'll need to make some variational approximation to. Distributions that are under our control and typically with learned parameters, I'll notate with letters other than P, and generally there'll be some mnemonic there. So E of Z given X would often be written as E sub theta or P sub theta or Q sub theta of Z given X. Here E stands for the encoder, and I'll be dropping the reference to the parameters because it just makes for notational clutter, and given that it's not a P, we'll know that it can have parameters that are learned. Similarly, we could have C of Y given Z, where C will stand for like a classifier in general, as like an example. But Y doesn't have to be labels. It could be, another image if we were doing, if we were learning a generative model of images, for example. And that could have learned parameters, or similarly, B of Z given Y, where B stands for its backwards encoder. This is going to be distribution over Z that we get from looking at the targets Y rather than the observations X. Great. So now I want to spend a little bit of time looking at maximum likelihood and demonstrating that maximum likelihood is equivalent to information maximization. So starting with what maximum likelihood looks like, this is a common way to write maximum likelihood on two variables, X and Y. And so in maximum likelihood, we're trying to find the model parameters theta, such that the expected log probability of the observed data, X and Y, is as large as possible. And so there's a dissection of the maximum likelihood formulation so if you weren't familiar with it before, hopefully this is a helpful way to understanding it. Okay, so the first thing that we'll do is we'll just start with this modeling assumption that we can, instead of writing this as P of Y given X and theta, we'll say that there's we're going to have some intermediate representation Z, and that will parameterize that with theta. And if we take the integral then over all of the Z's, then there's some true P of Y given Z that will give us the same answer as our original model. And this is, I say this is a modeling assumption, and maybe it seems a little bit weird. There's two reasons for this modeling assumption. The first is that in deep learning, this really is what we're doing. We have some, typically there's like, if you imagine just a feed-forward neural network, a ConvNet or an MLP, you're just stacking a series of functions, and the only way to get to the final output, which is some distribution over y, our target variable, is to compute all of those functions in order. And there's like maybe there's like skip connections in the middle or something, but there's some point at which you get to a layer where you have a set of activations. And the final output is only a function of those activations. So this writing things this way, writing our saying that we have a distribution over z, given that we saw the observation x, is like reflecting the reality of what we do in deep learning. But this is also, this doesn't require deep learning in order to still be valid. We could say that for like, if we just had a linear model, for example, we could say that this encoder, P of z given xi and theta, is actually just going to be an identity function. So actually z equals x in that setting. But that's not really the setting that we're going to be interested in. In modern machine learning, we use deep networks for most things. So anyway, so this is the idea behind this modeling assumption, that we're going to just rewrite this, assuming that there's some intermediate representation z that will ultimately be used by to classify, to like estimate the probability of a particular output. So given that modeling assumption, we can rewrite that using that encoder notation, notation that I described on a few slides ago, where P of z given x and theta is equivalent to just this encoder z given x, which has some learned parameters theta that I'm omitting. So these two things are exactly equivalent, it's just different notation. Having done that, we can pull this expectation, instead of writing the log of the expectation, we can write the expectation of the log, and that's not going to be an equality, that's going to be an inequality that's known as Jensen's inequality, which says that the expectation of the log is less than or equal to the log of the expectation. So we have an inequality here. And given that, then let's rewrite this integral as just an expectation over the variables involved. So we have an expectation over samples from, we have an expectation over the distribution over the joint distribution of x and y, and our encoder distribution E of z given x of the log probability of P of y given z. And then let's multiply by 1. We'll multiply by some arbitrary distribution that has the correct form, C of y given z, and divide by it. So this is just a multiplication by 1 of any distribution of our choice that's over the correct random variable. So having written it like that, we can actually extract a Kl divergence. The Kl divergence in this case is going to be P of y given z between P of y given z and C of y given z. And then that leaves us with this expectation of over the same distributions as before of the log of C of y given z. So Kl divergence is non-negative, as I told you earlier. So if we just subtract that non-negative number, we get another bound. What we get out is smaller than what we had before, but we no longer have to worry about. We have now gotten rid of this distribution P of y given z that we didn't know. That we know it exists, but we don't know what it looks like. So now we have something that we can write as a cross entropy. This is the cross entropy here is going to be it's actually a negative cross entropy of y given z using this cy given z guy. And so this maximizing the negative cross entropy is the same as minimizing the cross entropy, of course. And all of you, I'm sure, are very familiar with minimum cross entropy as an objective function, and you probably are aware that this is the most commonly used formulation of maximum likelihood. So because of Gibbs inequality, again, that the cross entropy is greater than or equal to the entropy, we can replace that cross entropy just with the the true but unknown entropy value in this. And because it was a negative cross entropy, that means that the thing above is less than the thing below here. And now if we just add and subtract the entropy of y, which is constant with respect to the parameters of our model, we get IYZ minus the entropy of y, which has the same maximum value, the z that maximizes this is the z that maximizes this, which is the same z that we would get from the parameters of our model that we incorporated into our encoder. So that's the negative cross entropy is a lower bound on both maximum likelihood, the maximum likelihood objective, and on information maximization.
Okay.
So yeah, so that was a lot of stuff. So
I got some question from the audience. The first question is from Mr. Dedi Rahman Wijaya. The question is, which is better, original mutual information or normalized mutual information?
Sorry, which is better, the mutual information or the normalized mutual
information or normalized mutual information? Which one better?
Yeah, so I'm going to guess that normalized mutual information. So there's a few different ways to talk about normalizing mutual information. A common variant is Jensen's Shannon divergence. Is one way to take a mutual informations and turn it into a normalized value. There's another way you can because of the bounds on the mutual information, you can trivially just divide through by the entropies if you know them. Normalizing the mutual information gives you it has a requirement that you know whatever value it is that you need to normalize against, and this can be a difficult constraint to a challenging additional constraint for the problem you're trying to solve. But if you happen to know that normalization because you're doing the Jensen-Shannon type thing, or you happen to know the entropy of the bounding entropy, then that might not be a problem. But it does make the problem slightly more challenging in many circumstances, and it also removes the really critical aspect of these information measures, which is that they are measures. It removes measures. and they have units. I don't want to tell you that you should never use a normalized information measure. That that's kind of a strong opinion to state. I would say that there are a lot of advantages to using the information measures as like Shannon defined them. It maintains this additivity. It has units that are meaningful, and it's often like pretty easy to work with in information in a machine learning setting.
Okay. The next question is from Mokwe. The question is, I might have missed this point, but where or when is information theory technique applied in machine learning?
So the stuff that I have here on this slide shows the most common application of information theory to machine learning, which is that this cross entropy loss, the cross entropy objective that powers basically any classification that you've probably ever, any classifier model that you've probably ever trained, is an information theoretic loss. I mean, let's say the cross entropy is an information theoretic quantity, so that's probably unsurprising. But I haven't actually gotten to what I'd consider the good stuff. So the remainder of the talk will hopefully address that question.
Yeah. Okay, the next question, maybe this is the third question is, in implementation, what is the effect of Kl Divergence? What is the effect of Kl Divergence?
What's the effect of the Tail Divergence?
Yes.
In the implementation, is that what?
Yeah, implementation. Yes.
In the implementation, what is the effect of the Tail Divergence? I'm not certain that I fully understand that question, but I'll take a stab at it. So the Kl.
Yes, you mean maybe in application, maybe, or something system, or anything else, maybe something like that. Yes.
So because the Tail Divergence is core to like these to the mutual information. Anytime we're estimating the mutual information, we'll be doing that with the Tail Divergence, and that Tail Divergence is going to be then assuming that you're doing gradient-based optimization using backprop, for example, like all of us are probably doing in deep learning these days. The Tail Divergence is going to be the thing that gives us our gradients. So if you, I mean, like the Tail Divergence is going to show up in these objective functions that I'm discussing. In most of the objective functions that I'm discussing, because information terms bounds on mutual information are going to show up. And so like the impact is that the Tail Divergence that we're looking at will give us like the types of models that we're trying to get, these ultimately hopefully more robust models.
Yes.
Okay.
Maybe you can pursue your slide, but I remind you that your times take around 40 minutes again. So please, but I remind you also that maybe last 15 minutes, I think for the question is better for audience to ask you, okay?
I'll definitely leave some time at the end. Okay, great. So this was kind of a lot of derivation to throw at you in slides, and I hope that this is useful for those of you who are interested in studying this stuff in the future as more of a reference, rather than I don't actually expect you to perfectly follow this. Okay, so actually, so I'll talk a little bit more about maximum likelihood. The Markov chain, the underlying Markov chain in maximum likelihood is actually, it looks like this. The thing that we actually have is this distribution x and y, and so the universe gives us some relationship between x and y. And the thing that we're trying to get in order to like do something in order to learn something, our modeling task here, we only get to actually look at x, and that gives us to get this representation z. So our Markov chain, like z and y are conditionally independent given x. Which again is the same thing as saying that the joint distribution p of x, y, z factorizes as p of x, p of y given x, e of z given x. And so this is what this is the structure that we actually have to use at inference time and to use while we're learning. But what we want, what we're hoping for, is a Markov chain that looks like this, where z, our representation z, actually makes x and y conditionally independent. So there's some desired distribution q of x, y, z, where it would look like p of x times e of z given x times our classifier c of y given z, and that's what we'd like to get to. So by the data processing inequality, given these Markov chains, we know that IYZ, the mutual information between y and z in our actual Markov chain, is less than or equal to the mutual information between x and y. So maximum likelihood, this means that maximum likelihood is learning a representation z that maximizes a lower bound on IXY. In the previous slide, in the derivation here, I showed to you that it's actually, we have a bound on IYZ. And so this data processing argument and proof that I just gave you shows that this lower bound on IYZ is also itself a lower bound on IXY. And so sometimes, actually, a lot of authors will talk about directly maximizing some bound on IXY. I think that it's actually a lot more illuminating and fruitful to think in terms of these representation variables that we're learning, and understand that we're actually bounding the information quantities between our observed variables and that representation z. But in at least some cases, if probably almost all cases actually, those bounds using the representation z are themselves bounds on the mutual information between the observed variables. Okay, so given that understanding, there's like different possible outcomes for z. So one possible outcome for z in this kind of set diagram notation is that z exactly covers all of the elements of the set that live here in the intersection between x and y. And this is all that's required for z to satisfy the target Markov chain, because this is all that's this is all that's necessary to have z perfectly. I've now dropped the term. Perfectly mediate between x and y. As it turns out, the actual outcome for z is that with maximum likelihood is that z just captures all of the information about x. It ends up completely covering x, and the reason for that in standard neural networks, for example, doing maximum likelihood with standard neural networks, is that these functions are deterministic and not particularly lossy. So like I'm maybe slightly exaggerating, but there's almost no information loss if you have an unregularized neural network. There's almost no information lost in Z, which is a continuous variable representing, typically a discrete input. Even if it's, images, those images are technically discrete. So this continuous function will happily retain all of the information about X in the service of solving this problem of predicting Y. So like maybe that's okay. Maybe it's bad. I'm not giving any comment one way or the other. Just pointing out that there are two different possibilities that two different extrema that would both satisfy that target Markov chain, and maximum likelihood chose one of the two, the one where Z is basically going to memorize X. Okay, so in summary, for this kind of analysis of maximum likelihood, if you,
Sorry, Jan.
Yeah.
Do you change your slides or page maybe, but any audience asks you that the slide is frozen?
Oh, no.
Sorry.
That's...
you can reshare again your slide maybe?
Yeah, I will do that. Okay, so...
Yes, reshare again. It's better.
Okay, so...
Sorry. Yeah, sorry bother you.
Yeah, thank you for letting me know. Okay, so we will share that.
Yes, this one's better.
Okay, so at what point did the slides freeze? Because like a lot of that would have been confusing if you couldn't see the changes in slides. Can you just tell me which slide it was on?
Maximum likelihood, yes.
When you stop, when you explain about Kl divergence, the ones with the many equations.
Oh, wow. So everything that I said,
this one. Yeah.
Here, you guys
yeah.
changes. Oh, yeah. Okay. So I'm sorry about that. And thank you for letting me know. Please stop me quickly if that happens again.
Yes. Please take a copy.
Okay. So I will I'm going to run through these again because otherwise a lot of things, you won't have the correct context here. So, okay. So the actual Markov chain I was saying is this Markov chain where the observed distribution that we have is that X goes to Y. That's fixed. The universe gave us that, and then we're learning some function Z. It's some function of X only that gives us a representation Z. And so that means that the joint distribution P of X, Y, Z is going to factorize as P of X, P of Y given X, E of Z given X for our encoder. And the Markov chain that we wanted is that X goes to Z goes to Y. We want to be in a situation where Z completely mediates the relationship between X and Y. And so we can represent that and say there's some desired distribution Q of X, Y, Z, which is equal to P of X, E of Z given X, and C of Y given Z are like learned classifier. That's the thing that we wish we had, but what we actually have is the upper setting. And so in the true setting, the upper line here, by the data processing inequality, we know immediately that IYZ, the mutual information between Y and Z, is upper bounded by the mutual information between X and Y. And so that means that maximum likelihood is learning a representation Z that maximizes a lower bound on IXY. And so again, that was in this slide with all the math, the bound that I showed is that the maximum likelihood is a lower bound on IYZ, or maximum likelihood is equivalent to maximizing a lower bound on IYZ. And so what I'm showing here is that it's also equivalent to maximizing a lower bound on IXY because of the data processing constraint where IYZ it must be less than or equal to IXY in the true Markov chain that we have. So yeah, so then what I was discussing, these different possible outcomes for Z. Z in our set diagrams can look like this, where Z is exactly covering the all of the set elements that are at the intersection of X and Y. And that's all that's required for Z to satisfy this Markov chain, X to Z to Y, where Z is mediating X and Y. But the other possible outcome for Z, the other extrema, and this is basically the actual outcome for Z, is that Z completely covers all of the information in X in order to solve this problem of maximizing a lower bound on IXY. And so, like, maybe that's okay. At this point, I'm not going to express an opinion on the matter. But it is worth understanding that there's actually, you know, two very different possible outcomes that both would satisfy the thing that we're trying to get, which is a representation Z that is useful for solving this problem that we care about. Okay, so to summarize, then, if you use standard maximum likelihood approaches, you're already using information theory to train your models. The cross entropy is an information theoretic objective, and it can be simple to reframe a parameter-oriented approach like maximum likelihood as a representation-oriented approach. And what I mean by representation-oriented is that instead of worrying about the parameters of the model theta, we'll just think about expectations over some variable Z, where, like, each X, each observation X, or each target Y might have might entail some distribution over Z. Maybe it's a deterministic function, so it's but that's still a distribution. Or it could be stochastic, and obviously that's will be a distribution as well. And maybe the distributions are explicitly parameterized by the model, or maybe they're implicitly parameterized by the data. And we'll see examples of both of those. But because of the fact, like, just practically, because of the fact that we're using these deep networks, this is a very natural way of thinking about things. It's just some internal representation per example that you look at. There's each example entails an internal representation of the network, and we can just call that that representation Z, and work with that representation rather than thinking about model parameters. And finally, maximum likelihood approaches without regularization will try to memorize your training data, which may or may not be a problem. Okay, so yeah, okay, so I'll just, we lost a little bit of time there, so I'll plot forward here. So for maximum likelihood, we saw that we are maximizing this, explicitly we're maximizing this mutual information, a bound on this mutual information IYZ, which we can write in the derivation that I showed you. We can write that explicitly as maximizing h of y minus h of y given z, where h of y given z is it being bounded by the entropy of our classifiers, c of y given z, and h of y is a constant. But mutual information is symmetric in its variables, but there's two different ways to write it in terms of entropies. So instead of doing that, we could try to find a way to maximize IYZ, writing it as h of z minus h of z given y, which also has the same property, that it's going to be lower bound on IXY. And so this is what some more recent approaches in Infomax do that you may have heard of. There's one called Deep Infomax, and I think better known is this one called Contrastive Predictive Coding. And the advantage of these type of approaches is that we never have to generate Y. which means that we can use it really for any type of data that that we want to be able to do predictions over. In the case of a classifier, generating Y isn't such a big deal. You're generating there's K classes. You're generating you're just having to generate a vector of K values, K scalars. And that's not that big of a deal. But if you instead are like working with images or with videos, and your training procedure requires you to directly compute the log likelihood of the target variable Y, that can become very, very expensive. Just because a video, doing this for like a video, of course, that's like that can be many hundreds of megabytes per example. So instead, being able to work directly in latent space for the objective function can make a very substantial, give a very substantial gain in how efficiently we can learn things. So how do we do this? How do we lower bound IYZ just using entropies of Z? To work our way, we'll work our way up to that. So we'll start with an easier problem. Let's try to define a variational classifier that only uses distributions of Z. So we'll start out with just a definition of our classifier. We have some distribution P of Y given Z that we don't know what it is. And we can use Bayes rules to rewrite that. Bayes rule to rewrite that as P of Z given Y times P of Y over the marginalization of that pair, P of Z given Y prime integral dy P of Z given Y prime P of Y prime. And so because classification is discrete, we know that we can rewrite that integral as just this summation over all the different classes in the denominator, and then let's just go ahead and replace that P of Z given Y with some variational approximation. Not saying anything about a bound here, just that we're going to say that like there's some distribution B of Z given Y that gives us a distribution over Z, having looked at Y, that is under our control that we can choose. And if we replace P of Z given Y in both the numerator and the denominator, it gives us this thing that approximates P of Y given Z. Sorry, P of Z given Y. I'm sorry, B of Z given Y approximates P of Z given Y. And if we make both replacements, we get something that approximates P of Y given Z. And it's using, in the denominator, we have like this exact marginalization of the classification variable Y, because that's finite and discrete. And so we'll define that then as our classifier. And so like, why can we do that? Well, there's two things that we need. First is that C of Y given Z, this classification distribution, has to be a valid distribution. And it is. This is actually easy to see because this last step here is actually just a softmax of log B of Z given Y P of Y. So if you guys are probably all familiar with the softmax operation, which is just the ratio between the e to some function over the as the sum of e to that same function over all the different values that that you are marginalizing out. And so that's the same thing here. If we put a log, e to the log of this here, we just get out B of Z given Y P of Y, and if you had an e to the log of it here, the same thing. So this is just a softmax, so that means it's a valid distribution. And by the construction, by the derivation I showed you, it has the correct conditional structure. to match P of y given Z. So this is, in fact, a variational approximation to P of y given Z that we'll call C of y given Z. We call this the consistent classifier because it's a classifier that is consistent with some backwards encoder of our choice, B of Z given Y, by construction. Yeah, okay. So this is, this is hopefully a pretty simple to see way of getting a variational. We can choose this as a variational classifier that will, approximate the classifier that we want. So from this, let's loosen the restriction that we exactly marginalize out Y. So starting from the same setting, we want to have this P of Y given Z, and you can rewrite it in terms of P of Z given Y and P of Y. So now instead of doing an exact marginalization over P of Y, let's just assume that there are k different values of Y, each of which has equal probability of 1 over k. And we're going to look at just k of these at a time. So we can cancel out these 1 over k terms in the numerator and the denominator, since it's constant now with respect to the y variable that we're summing over. And then we can make the same variational approximation, replacing P of Z given Y with B of Z given Y in both places. And this is now also a this is now also a variational classifier. But C of Y given Z, instead of having exactly marginalized out all the possible Y, it's now just a valid. It's just this is a softmax. Excuse me, a softmax distribution over the mini batch of k examples that we're looking at. So I didn't say this up front, just kind of gave you a derivation, but basically what this is going to be useful for is we can take any set of y values that we want to compare against, and for all of the we'll take a mini batch of y values and their corresponding z values to compare with each other, and for each pair of y and z, we will compute the probability or the log probability of that y and z of the z given y, and then compute a softmax over all of the other z given y's in the mini batch. And for the same reasons as before, the softmax gives us a valid distribution, and it gives us a distribution with the correct conditional structure where we're actually this is a distribution over y given z, but it's not over all y's. So now it's only over the different y's that we saw in the mini batch. So yeah, this mini batch classifier that we just derived, C of y given z, has this interesting form, which is B of z given y over this marginalization of B of z given y, but without without any reference now to the P of y, because like the P of y is canceled. So if we divide by k in the denominator, now we actually get a uniform marginalization of B of z given y. So this is a different thing than what we're working with before. Here, here we have like a softmax classifier that we've derived, but just by bringing back in this 1 over k to capture the uniform distribution over the different examples in the mini batch, this bottom part now is actually a marginalization, a mini batch marginalization is how I refer to this, of this distribution B of z given y. And the top part is just our normal B of z given y distribution. So if we take a log, if we put a log in front of this, and then take the expectation over it, what we end up with is a variational approximation to the combined quantity h of z minus h of z given y. Because the mini batch marginalization is downstairs in the log, which is equivalent to minus the expected log of that marginalization, which is going to be a bound on h of z. And in the upper part of, in the numerator of the log, we have b of z given y, which so we have positive log b of z given expectation of log of b of z given y, which is a bound on h of z given y. That's the cross entropy. This will be a cross entropy bound on h of z given y, and then this mini batch marginal bound is the other one. Bounds the other one, but we got there only by adding this constant thing in. So if we minimize this thing and then add in log k to account for this, the whole thing is an upper bound on the negative of this, or a lower bound on this. So that was kind of a fairly complicated chain of reasoning, but each step is, I think, pretty simple and easy to understand. So if you look at the papers on CPC and Deep Infomax, or the variational bounds on mutual information paper, you'll see different derivations and proofs of this bound that may be easier or more difficult for you to follow. This is the one that I've found that I like the most. Okay, so that's how we get a lower bound. Oh yeah, go ahead.
Hello, Ian. Sorry,
Yes.
I remind you that your time can be.
Okay, yeah, this is a good
yeah,
stopping
5
point.
minutes, because the last 10 minutes or 15 minutes later, we will go to the ask and answer and question. Okay, so your time is 5 minutes. Again.
Oh, okay. So yeah, 5 minute morning.
Sorry. Yeah.
Can you still see me changing slides? Can I get a audible confirmation that like when I press the slide changed? I'm not hearing anything from anybody.
Yes. We can see the change.
Okay,
Thank
great.
you.
Thank you. Okay, so this derivation that I just gave you is for an objective that's called info NCE, for information noise contrastive estimation, and that's the objective function used by the CPC model, contrastive predictive coding. And so this is a tweet from the first author on the CPC work, who's showing where he's showing this this graph where if you pre-train an ImageNet model, a ResNet model, unsupervisedly using CPC, and then just fine-tune on a classifier, fine-tune the classifier afterwards, then you can get the same performance, or you can get better performance than a traditionally trained cross-entropy loss trained classifier using the same architecture with up to 80% pure labels. So this is the percentage of labeled data that they're using. So at 1% labeled data, their top one, their top 5 accuracies. These are top 5 accuracies. Their top 5 accuracy is around 78%. compared to 44% or something for traditional cross entropy loss. So they're showing that there's some really dramatic gains here that shows that semi-supervised learning can really work quite well using an objective like InfoNCE in a setting like CPC. But there's this question, is InfoMax really the thing that is causing these gains, or is it something else? And the very impressive results, but what's the actual cause? And so there's an interesting set of experiments done in this paper on mutual information maximization for representation learning that did some analyses of different variants of CPC and InfoNCE to try to understand better what's really going on. I think I'll try to just get through this set of things quickly here. So the experimental setup that they have is that we're going to have MNIST digits. I'm going to show pictures of a lake, but instead they're actually using MNIST digits, and they split it into a top view and a bottom view. So this red rectangle is the top view, and the orange rectangle is the bottom view. And the task is to predict the digits just by looking at the top view. And so if you just did a logistic regression looking at the top half of the pixels, you can get 85% accuracy. But what they're going to do is they're going to estimate this InfoNCE bound using X1 as the top half of the image as the first thing, and the bottom half as the other thing, and that's going to give them a representation that they can then use with logistic regression to look at the accuracy of the final the accuracy using that representation. So the first thing that they do is they use bijective encoder. So a bijective encoder is one that's completely lossless. There's no matter what set of weights you chose for your model, with a bijective model, the mutual information is maximized. And so what they find is that when you train these bijective models, instantaneously, within a few training steps, they've already basically gotten to the maximum value of the information estimator. But if you look at the accuracy over training time, the accuracy actually starts out at the pretty much the same as the logistic regression, but continues to go up over time in spite of the fact that the mutual information estimator has saturated. So this means that these estimators, this CPC estimator, is still favoring a quote unquote a good representation, even though every single solution that it's looking at, every single setting of the model's parameters maximizes the mutual information. So they looked at another experiment, is looking at an MLP, just an MLP encoder with skip connections. So if we initialize these encoders close to identity, then at initialization, again, the mutual information is maximized, and there's no reason, if we're just have a bound on mutual information that we're trying to maximize, there's no reason to really change the parameters at all. So we would expect to see that the Jacobian of the parameters would be at 1, I think, for the entire time. But instead, actually, the Jacobian ends up having this quite broad distribution of values of the parameters. So even though we started again with something that maximized mutual information, the model prefers to change those parameters. The objective prefers to change the parameters of the model such that they quite dramatically away from those initial identities that maximize the objective. And doing so, of course, in this setting also continues to improve the classification accuracy over training. So these estimators are preferring non-invertible mappings, even when initialized to identity, which maximizes mutual information.
Sorry, Peter. I remind you that your time's maybe 2 minutes again. Okay. Sorry. Very sorry.
Yeah, let me. There's just two more slides here.
So, 2 minutes. Okay.
So and then we'll be at a good stopping point. So the third experiment here, looking at the what they call the critic, where if you have a more hypothesis, if you have this a more complex critic architecture, then we should have tighter bounds on the mutual information and therefore a better representation. And so what they show here is that in fact is the case. The blue line is the most powerful model, and the red line is the least powerful model. And so there's this clear ordering between the three models in terms of the bound on the mutual information. But the actual performance of these models is the opposite. The most powerful model gets the worst accuracy, has the hardest time optimizing. The least powerful model gets the best accuracy. So more complex critics does give tighter bounds on the mutual information, but it gives worse representations. So I'll close with this thought here, which is when we're doing maximum likelihood, we get this outcome where we've memorized Z is memorizing X. But when we're using Infomax, the apparent outcome here is that Z is no longer memorizing X. But that's the common thread of those experiments, that's not the opinion. This is not what the authors were going for when they wrote that paper. They had a different perspective, but all of these experiments are consistent with Z actually having actively doing this Infomax influence the E objective is causing the models to learn a Z that is actively throwing away information about X. So these Infomax models are accidentally, I think, certainly accidentally compressing.
Sorry, Mr. Maybe.
Yeah, this is it. Yeah, so the question that I'll leave is this compression a good thing? And can we measure it and control it somehow? And so that's where we'll pick up tomorrow.
Very sorry, this is the limitation of time. So we have 3 questions for the last session. And the first question from Simon. In practice, what is your choice for MI estimator, especially if we wish more stable computation and better results, say for representation learning?
The question is what's my preferred way of what's my preferred objective function? I think basically what's my preferred estimation technique for these mutual information quantities. That's what I'll be discussing tomorrow. We'll get into alternatives here. So what I've shown today is basically things that are equivalent. In theory, things that are equivalent to maximum likelihood, which is this information theoretic view on maximum likelihood and this Infomax stuff, which in theory should be equivalent to maximum likelihood, but it clearly is not doing exactly the same thing. So we'll get into that question really tomorrow.
Okay. The next question is it correct to assume that X are data and Z representation, and why the task? That is correct?
Yeah, that's So I showed that in the notation slides, where so I called X observations and Y targets and Z representations. So the thing that you're calling tasks in the question, I was calling targets, and the thing that you're calling data, I was calling observations. But yeah, that's exactly right.
Okay, the last question. With reference to papers, so in your previous slide, a new finding in SIM CLR version 2 paper is that bigger model with a wider scanner yields the highest accuracy in a contrastive-based pre-training. Can you elaborate on this, please?
So the audio was a little bit problematic there. So it said that the paper said that wider models with what?
Models SIM-CLR.
Yeah, I'm sorry. Actually, could you just read the question again? The audio was a little bit broken.
Okay. A new finding in SIM-CLR version 2 is that bigger model with wider kernel yield the highest accuracy in a contrastive based pre-training. Can you elaborate on this?
Somebody pasted it in. Okay, great, thank you. Yeah, so the things that I was just saying in these slides, this set of experiments. So these are like different from these questions are different from model capacity questions. These are there's a bit of a subtlety there that I don't think we'll be able to really get into here. But for all of the techniques that I'll be talking about, having a larger model, for all the techniques I'll be talking about tomorrow, having a larger model basically uniformly improves performance on the tasks that you care about, whether it's classification or whatever. And this is I guess consistent with kind of standard deep learning finding at this point that if you just make the model bigger, things get better. And why is that, given that we know that maximum likelihood tries to memorize. So the alternative objectives we'll be talking about will have that same property, that larger models are better. The paper that you're referring to appears to be finding the same thing. They're asking a different question than the ones this paper that I was just describing were asking, which was if you made there's kind of a difference between the number of parameters in your model and the actual probabilistic modeling choices you're making. So this paper was asking questions about making more powerful probabilistic modeling choices rather than just adding more parameters.
Yes, that's all the question, and I think the time is over. And before we close to this session, could you conclude of your talk today? Okay, could you conclude of your talk?
Yeah. So the conclusion is that there's more tomorrow. Today was setting up the stage. Again, the title of this talk is Information Theoretic Objectives and Robust Generalization. Today we've gone through some of the most popular information theoretic formulations of objective functions that are out there right now. Tomorrow we'll start looking at things that are not as well known, but are gaining some popularity because of their really remarkable results, in particular in robustness. And so I'll be defining. I'll be talking more about this idea of measuring and controlling compression tomorrow, and defining what I mean by robust generalization, and how we can measure how well we're doing at that tomorrow. So there's quite a bit more content tomorrow that won't be it won't really be background content anymore. It'll be much more current state-of-the-art research.
Okay, thank you, Fisher. But the last request, I would like taking picture together. So please, the audience, open your switch on your web camera. And sorry, Fisher, could you close your slides?
Oh yeah.
Sorry, thank you for the slide. Okay, I would remind you. Okay, taking all. Wait. Switch on your web camera. I would like to take the picture. 1, 2, 3. Wait. Okay, once again for the next page. 1, 2, 3. Okay, thank you very much for your time, and we will go to the next session. And thank you very much to your talk, Peter, and see you again in next time. And I'm Risnader. Today, our session is closed, and bye-bye. Thank you very much for your attention, and
Thank you.
bye-bye.
Okay, bye-bye.
Bye-bye.